We know how to launch starships in theory, but can we make one that actually survives 100 years in deep space? At 1/10th light speed, dust shreds the hull, radiation scrambles computers, and life support grinds itself to death. In this video, we'll tear through the ship, system by system, to find out what really fails first. But before we continue, please subscribe to the channel if you enjoy the video. Let's continue. The first part of your starship that really starts to lose the fight is not the engine or the reactor. It is the front wall slowly being eaten away by space itself. That sounds dramatic, but at 1/10th the speed of light, your hull is under constant attack from matter you cannot even see with your eyes. Space between stars is not empty, it is just very thin. On average, you get about one atom in every cubic centimetre, plus a smaller number of dust grains. That does not sound dangerous until you add speed. Your ship is moving at about 30,000 kilometers per second, roughly 67 million miles per hour. At that speed, even a tiny piece of dust hits with extreme energy. Take a grain weighing 1 milligram, much less than a pinch of table salt, and slam it into the hull at that speed. The energy released is in the same ballpark as a hand grenade going off in contact with the metal. One grain, one blast. Now spread this out over a full century. The front of your ship, the part facing into the direction of travel, is under this constant rain of high-energy hits. Most grains are much smaller than a milligram, but the total number of impacts is huge. Each one melts or vaporizes a tiny bit of material, sends fragments away, leaves a crater. Over 10 years, the change is small. Over 100 years, the nose of the ship is measurably thinner, rougher, and structurally weaker. The hull is not just resisting pressure, it is also slowly eroding, millimetre by millimetre. So how do you keep the main hull from being shredded by that dust when turning around or slowing down is not an option? You do the same basic thing we already do in Earth orbit. You put sacrificial shielding in front. Engineers call this a Whipple shield. It is simple in concept. You put a thin outer plate in front of the real wall with some empty space between them. A small particle hits the thin plate first, breaks apart, turns into a hot spray, and by the time that spray reaches the main wall, the energy is spread out. At speeds up to around 15 kilometers per second, about 9 miles per second, this works very well. That is why satellites and the International Space Station use it. But your Starship is not going at 15 kilometers per second. It is going at 30,000. That is more than 1,000 times faster. Because the energy in an impact scales with the square of the speed, 1,000 times more speed means about 1,000,000 times more energy per unit mass. At that level, a dust grain does not just poke a small hole, it vaporizes the first plate and can also tear into the main wall behind it. The classic Whipple design was never meant for this regime, so the forward shield for a Century ship has to be something else. A thick, heavy, replaceable block of material. It might be several meters of water ice, or piled rock from an asteroid, or layers of metal foam. The goal is to have a big mass in front that can absorb these hits over decades. Each impact takes a tiny bite out of that block. Over time, the surface recedes. If the designers guessed the dust density in deep space too low, if they undersized the shield to save mass, then after 50 or 70 years the protection becomes too thin. The crew in year 70 is then flying behind armour-sized for a mission that was too optimistic. That raises a direct question. Even if no dust ever hit the ship, could the hull itself handle 100 years of spinning, flexing, and thermal cycling without cracking from the inside out? The hull of a rotating starship is not just a static shell. It is under constant repeated stress. To give the crew 1G, without intense nausea, you probably run a large ring at a gentle spin, around 2 to 3 revolutions per minute, with a radius of a few hundred meters. 3 spins per minute is 180 per hour, over 4,000 per day. Across 1 century, that adds up to about 1.6 billion complete rotations. Every single rotation stretches and relaxes the ring structure a microscopic amount. Metal does not like endless cycles like that. Airplane wings, turbine blades, bridge cables, they all have a fatigue life. Even when the stress is below the level that would snap them in one instant, repeated cycles slowly grow micro. Cracks. These cracks tend to start where the stress is a bit higher than average, around hatch corners, welds, bolt holes, cutouts for windows and ducts. At first, the crack is too small to detect. Over millions, then hundreds of millions of cycles, it grows. Once it reaches a critical size, one more normal load can cause a sudden fracture. In a rotating habitat ring, that could mean a local panel failure. Or in a worst case, a cascading break that forces you to reduce spin for safety. We already have proof in orbit that long-lived pressurized structures are not set-and-forget hardware, even at much lower speeds and shorter timescales. The International Space Station has only been permanently crewed since the year 2000, and it flies in low Earth orbit at around 7.7 kilometers per second, about 17,000 miles per hour, far slower than an interstellar run. Even so, engineers on the ground track small structural issues all the time. In 2020, controllers noticed a slow loss of air, measured in grams per hour, that built up over months. The crew had to close hatches, isolate sections, and use ultrasonic sniffers to trace the leak. The final culprit was a crack only a few centimeters long in one of the Russian modules. That crack existed in a station with heavy monitoring, fresh parts delivered by cargo ships, and eventual rescue options. Your 100-year Starship has none of that support. There is no ground team sending spare modules, no emergency shuttle waiting on a pad. You launch with what you have, and you must make it last for generations. That is why structural health monitoring on a Sentry ship is not a nice extra. It is essential life support. You cover the hull with strain gauges, mount acoustic sensors that listen for the tiny ping of new cracks forming, run fiber optic lines through beams to watch how they bend under load. The structure constantly reports its own health into your computers. Here is the twist. The metal may outlast the instruments that watch it. Strain gauges are just thin films glued to surfaces. They peel or drift. Acoustic sensors age, their sensitivity drops, or their electronics suffer from radiation damage. Connectors corrode. The data channels that move all that health information back to the computers pick up noise, bit errors, and dropouts. Over decades, more and more of your monitoring network becomes unreliable. That leads to the first real structural failure mode on a Starship like this, the loss of confidence in your own measurements. Picture a future maintenance team, 2 or 3 generations after launch, looking at their dashboards. Some sensors on the forward shield show rising stress, others show flatlines, others have gone completely dead. Which ones are telling the truth? Which ones have simply aged out? Do you divert power and mass to add more shielding, or do you assume the scary readings are just sensor drift? If you get that judgment call wrong, you either overreact and cripple the mission, or underreact and fly into real danger with a weakened hull. And while the outer shell is fighting dust, fatigue, and failing sensors, another threat is soaking the whole ship, including the electronics that need to stay sharp for a full century, a constant storm of high-energy radiation that never ever turns off. The metal skin can be patched and thickened, but how do you armor yourself against something that goes straight through meters of steel, barely slows down, and still hits your brain and your computers? Away from Earth's magnetic field, your ship sits in a constant drizzle of high-energy particles, mainly galactic cosmic rays. These are protons and heavier nuclei fired out by supernovae and other violent events in the galaxy, moving at a large fraction of light speed. If an astronaut just floated out there with no shielding, they could get roughly between 0.6 and 1 sievert of radiation dose per year. In simple terms, that is enough that a single Mars round trip is already close to the career limit dose NASA sets for astronauts over their entire life. Do that dose for 3, 4, 5 years, cancer risk climbs hard. Stretch it to 10 years or 100, and unshielded human bodies are not in the game at all. So you add shielding. Put tens of grams of material in front of every square centimetre of crew area, which translates to a few centimetres of aluminum, or a similar thickness of water, or plastic rich in hydrogen. In metric, that might be 5 to 20 centimetres. In imperial, 2 to 8 inches depending on your design. That cuts down a lot of the lower energy particles and reduces the total yearly radiation dose significantly. But it does not drive the dose to 0, not even close. The highest energy cosmic rays laugh at your hull. They pass through, lose a little energy and keep going. Over a century, even with heavy shielding, the crew and the electronics live in a slow, steady bath of damage. Now, if you think, fine, I'll just pile on more metal, there is a catch hiding in the physics. When a very high-energy cosmic ray hits a thick layer of heavy material, like aluminum, it does not just stop cleanly. It smacks into the nuclei of the atoms in your shield and creates a shower of secondary particles. You can get neutrons, lighter nuclei, and fragments that spray in many directions. Some of those secondaries can actually be more biologically harmful per unit energy than the original particle, especially neutrons, which penetrate and interact in different ways inside human tissue. Put around 20 grams of aluminum in front of each square centimetre, roughly 7 centimetres thick, or about 3 inches, and you definitely block more of the low and mid-energy stuff. But for the most energetic cosmic rays, you also increase the number of these secondary particles entering your habitable volume. So extra metal has diminishing returns, and after a point, it can even change the mix of radiation in a way that is not purely better. That is why people talk a lot about hydrogen-rich materials, water walls, or fuel tanks as shields, because lighter elements tend to produce less nasty secondary showers. All of this does not just hit people, it hits electronics. That is where the long mission really starts to hurt. Spacecraft already use radiation-hardened components. Deep space probes like Voyager, Galileo, and Cassini carry chips built to survive tens of thousands to hundreds of thousands of grays of total ionizing dose. That sounds huge, and for short missions or even multi-decade missions it works. But those ratings assume a certain flux over a certain number of years. Your 100-year Starship is running many times longer, in a radiation environment that may be harsher than anything we have flown through so far. Inside each transistor in a chip, charge can get trapped in the insulating layers. Over time, this changes the voltage at which the transistor switches on and off. It is like slowly changing the rules for what counts as a digital 0 or 1 inside your CPU or memory. At first you see a few soft errors, random bit flips in memory that error-correcting codes can catch and fix. As the dose keeps building, threshold voltages drift more. Some transistors start to stick, some paths slow down. Circuits that passed all their tests during year 1 begin to behave strangely by year 30 or 40. If you lean on a single main computer core, it might start to die before year 50. That is why any realistic design for a Sentry ship needs not just spares, but a plan to rotate hardware out of the highest flux zones, and maybe periodically anneal it, warming it up to help release trapped charge. That is complicated, power-hungry, and still not a perfect reset. You can see early hints of this slow decay in the spacecraft we have now. Voyager 1 and Voyager 2 launched in 1977. They have spent decades crossing the outer planet's harsh radiation belts, and then the boundary into interstellar space. They are not protected by thick shields, just modest housings and distance. Today, almost 50 years later, they still talk to us, but their instruments and computers show more and more weird behaviour. Random instrument lockups, corrupted data packets, systems that work for months then suddenly spit out nonsense until ground controllers find a workaround. That is exactly what you expect from accumulated radiation damage layered on top of plain old aging components. On your Starship, this does not break the reactor first, or the big drive coils. Those are bulky, simple, and heavily shielded. Radiation goes after the quiet, delicate parts. It flips bits in DRAM. It injects spurious signals into analog sensor lines. It slowly kills the star trackers that watch the sky, darkening pixels in their cameras. It pushes reference voltages and precise timing circuits out of their calibrated ranges. At first, you barely notice it. Error-correcting memory masks most of the flips. Redundant sensors can vote and filter out the bad readings. Then, after a few decades, more permanent faults pile up. Some memory cells are no longer just occasionally wrong. They are stuck wrong. Some lines on a processor bus are noisy all the time. Calibration tables for sensors have to be updated again and again, compensating for drift. Software written by people who launched long ago, was never fully tested for this exact combination of partial failures. You start to get rare, hard to reproduce bugs, a navigation solution that jumps for a second, a radiation detector that occasionally reports impossible values, a guidance system that resets once a year, then once a month. From the crew's point of view, the first big radiation failure is not bodies dropping. It is trust dropping. You look at a star tracker reading, and you are not sure if the glitch is outside the ship or inside the sensor. You see a bit flip in a critical computer, and you wonder if your error correction silently missed any others. You run health checks more and more often, but those checks also depend on hardware that has been getting cooked by cosmic rays for half a century. This is how you can end up in the most dangerous state of all, where the engines still work, the hull is still mostly intact, but your information is compromised. You are still moving at a huge fraction of light speed, but your ability to know exactly where you are, which way you are pointing, and how healthy your systems really are, is crumbling under a storm of invisible particles that never took a break. If radiation can slowly corrupt the brain and nerves of the ship like this, what does that do to the systems that have to run for a century with spinning parts, valves, and propellant? The parts that actually push the ship and correct its course. Radiation slowly scrambles your ship's brain, but propulsion decides whether you can still steer the body at all. So how do you build engines and propellant that do not quietly die long before the mission clock hits 100 years? Start with the simplest question. How do you even keep your fuel in the tank for that long? Chemical propellants like liquid hydrogen and liquid oxygen only stay liquid if you keep them extremely cold. Liquid hydrogen sits down around minus 253 degrees Celsius, about minus 423 Fahrenheit. Even with very advanced insulation, you still get a little heat leaking in. That heat slowly boils the liquid into gas, and unless you constantly recool and recompress it, that gas has to be vented. You are losing a fraction of a percent every month. Over 10 years, that is bad. Over a century, it is a disaster. Your tanks would be mostly empty. You might say, fine, skip hydrogen, use storable propellants like hydrazine or nitrogen tetroxide, the stuff satellites use today. Those are liquids at room temperature, no boiling off. But they have their own timer. They slowly decompose, they corrode tank walls, they seep past seals. Even if the leak rate is tiny, over 100 years, the total loss adds up. A valve that weeps 1 drop a week is a serious leak when you wait long enough. So a serious century ship design is forced into a corner. Either you do not rely on big cryogenic tanks staying full for the whole trip, or you accept that chemical propulsion is just for short bursts, at the start and the end. For long cruise, you go to systems that do not care about boil-off, like nuclear thermal rockets that store solid fuel, fusion drives that eat pellets, or external systems like laser sails and magnetic sails. A beamed power light sail has no onboard fuel to leak at all, but it hooks you to the reliability of the laser infrastructure back in the home system. A magnetic sail uses the interstellar plasma itself as reaction mass, but now you depend on huge, delicate magnetic structures that also have to survive a century of hits and radiation. So even if you solve storage, you still have the engines themselves running for far longer than any engine we have ever built. How does that hold up? Look at the best case today. Ion drives. Deep Space One used an NS Star ion thruster for about 16,000 hours of operation. NASA's Dawn spacecraft ran its ion engines for over 48,000 hours total. That sounds like a lot, but 48,000 hours is only about 5.5 years of continuous use. Your 100-year ship needs effective thrust, or at least station keeping and course corrections, for something like 10 to 100 times longer. Ion thrusters slowly erode their grids, the surfaces that accelerate ions. The ion beam sputters atoms off the metal, widening holes, changing electric fields. Given enough runtime, the grid simply wears through. Now scale that problem to more extreme drives people talk about for interstellar travel, like fusion engines or high-power plasma rockets. Those chambers have to deal with very hot plasmas, intense neutron flux, wild magnetic fields. Every wall and every coil is under attack from high-energy particles. Each second of operation is like a tiny amount of sandblasting plus radiation damage inside your engine. It is very hard to see how you get a system rated for a few thousand hours now, up to a reliable, maintainable 100-year lifespan, unless large parts of it can be dismantled and rebuilt by the crew. That leads straight into the next ugly question. How many moving parts can you really afford in a propulsion system that nobody can replace from Earth? Any part that spins, slides, seals, or flexes is a likely early failure. Turbopumps in chemical rockets spin at tens of thousands of revolutions per minute, with tight clearances and very high pressures. On Earth, and in launch vehicles, those pumps are basically one-shot devices used for minutes. On a reusable ship, you would need pumps that start and stop many times over decades. Bearings wear, lubricants break down under radiation and vacuum exposure. Valves are just as bad. On current spacecraft, propellant valves can stick or leak after a few years or couple of decades. Articulation joints that steer nozzles dry out. Rubber seals harden and crack. A Century ship cannot treat any of that hardware as fit and forget. If a key valve cannot be rebuilt or remachined on board, it is a latent single-point failure. The first propulsion problems are very likely not the fusion core exploded, but something like this one critical helium pressurization valve will not open anymore. Or this check valve is stuck half shut and we can't get full flow. One frozen bearing at the wrong time can take out your ability to turn a thruster, which then kills precise steering. Even your backup power sources used to run engines and pumps are on the clock. If you use radioisotope thermoelectric generators, RTGs, based on plutonium-238, the fuel itself decays with a half-life of about 87.7 years. That means after one half-life, you are down to half the initial thermal power. After 100 years, you are roughly at 40 to 50% of your starting heat output. And the electrical part is even worse, because the thermocouples that convert heat to electricity also degrade with time and radiation. So the small quiet power source you thought you could always count on is slowly fading. Any emergency propulsion that depends on RTG power, like low-thrust ion engines for course corrections, has to be sized for that shrinking budget. Year 10 and year 90 do not look the same. Put all of this together and a pattern shows up. The first propulsion failure on a 100-year mission is not that you suddenly have zero thrust. It is that you lose precision. The big main drive might still be physically fine in year 90. The reactor is still hot. The coils still generate magnetic fields. The nozzle is still there. But several small things have gone wrong around it. Maybe some of the fine control valves for propellant have degraded, so you can no longer adjust flow as smoothly. Maybe a few gimbal actuators that point the engine are stuck so you cannot vector the thrust as accurately. Maybe your power system can no longer support running both navigation sensors and the engine at the same instant at full power. At that point, you can still do big burns, but you struggle with the tiny ones. You might no longer be able to trim your trajectory by centimeters per second. That sounds small, but over light years of distance, those tiny corrections are everything. A 1 centimeter per second error is only a small nudge now, but left uncorrected, it can grow into millions of kilometers of missats distance at the target star. So by the time propulsion fails in the way that matters, the ship may not be dead, it is just clumsy. You have a huge engine that can still push hard, but you have lost the fine fingers that let you steer with millimeter precision. Combined with aging sensors and radiation-hit computers, that is how you end up with a working drive on a ship that still might sail right past its destination, simply because it can no longer control its own power accurately enough. And if the system that pushes the ship forward and tweaks its path is already this fragile over 100 years, what happens to the smaller systems that simply keep you pointed the right way, pointed at your target star and at your faint communication beam back home? You can still fire your engines, but can you actually point them exactly where they need to go, year after year, when every part that controls your aim is slowly grinding itself to death? Attitude control is the quiet system that decides which way your ship is facing, where your antennas and radiators and drives are pointed. The workhorses here, on most satellites today, are reaction wheels. These are heavy spinning wheels inside the spacecraft. Speed them up, slow them down, and the ship rotates the opposite way. No thrusters needed. Simple idea, but the record in space is ugly. Missions like Kepler and several Earth observation satellites have been crippled or ended because just a couple of reaction wheels failed in less than 10 years. Bearings wear down, lubrication migrates or breaks down in vacuum. Tiny imbalances grow, until a wheel starts to draw too much power, vibrate or seize completely. Now stretch that to a 100-year mission. A wheel that is good for 10 years is completely useless as a permanent component. For a century ship, you either over-engineer the wheels with magnetic bearings, extremely low friction, and heavy shielding, or you admit they are consumables. Over-engineering means lots of mass and complexity, and it still does not magically get you from 10 years to 100. Treating them as consumables means you carry spares, or even better, you manufacture new wheels on board. But that means machining precise rotors, making bearings, balancing them to tight tolerances, and doing that in a flying workshop, not in a calm factory on Earth. If you fail at that, you slowly lose your torque authority wheel by wheel. So maybe you think about going bigger, using control moment gyros instead. These are like reaction wheels, but arranged to produce stronger torques by tilting spinning rotors. They are powerful. They can swing huge space stations like ISS around. But they come with their own trap, saturation. As you counter disturbances and change orientation, the gyros build up stored angular momentum. At some point, they reach a limit where they cannot give you any more torque in the direction you need. Then you have to desaturate them, dumping that stored momentum. Near Earth, you can do that using magnetorquers, which push against the planet's magnetic field with no propellant. Out in deep interstellar space, that field is gone. To unload your CMGs, you are burning real propellant with thrusters. Even tiny disturbances, a little off-center thrust here, a small asymmetry in radiation pressure there, add up over decades. If you mismodel any of that, your CMGs hit saturation more and more often. Every desaturation burn uses propellant, and that usage may be far higher in year 70 than it was in year 10. You also depend on accurate calibration. The software that decides how much to tilt a gyro or how long to fire a desaturation thruster needs to know the exact performance of that hardware. With aging sensors and mechanical drift, your attitude control loop can start to overshoot, undershoot, and fight itself, wasting even more fuel to stay pointed. But even if you had perfect reaction wheels or CMGs, there is a deeper problem. How do you know where you are pointed in the first place? That is the job of attitude sensors, mainly gyros and star trackers. High-end systems use ring laser gyros or fiber optic gyros. They have no spinning mass, they measure rotation using light, and they are very precise. But they still drift slowly over time. The drift is tiny day to day, but over a century, even a small bias, if not carefully estimated and removed, would build enormous pointing errors. Smaller, cheaper MEMS gyros, the kind you have in phones and drones, are even worse, they degrade faster, and radiation can shift their behaviour in unpredictable ways. Star trackers solve that by taking pictures of the sky, comparing star patterns to a catalogue, and telling the ship exactly how it is oriented. They are the eyes that reset the accumulated gyro drift. But those eyes are just cameras, usually CCD or CMOS sensors, sitting out there under a slow rain of cosmic rays. Every high-energy hit can knock out or damage a pixel. If you lose even a tiny fraction of pixels each year, after 50 years you are looking at a sensor full of hot pixels, dead pixels, and subtle sensitivity changes. Software can map those defects, ignore bad spots, compensate for aging optics, but that code gets more and more complex. By mid-mission, you are leaning on a massive stack of correction algorithms just to get a clean lock on the sky. One subtle bug in that stack, and your attitude solution starts sliding. We have already seen how fragile this chain is in low Earth orbit. The Hubble Space Telescope has had multiple gyro failures over its more than 30 years of service. Each time, and it lost some of its pointing capability until a space shuttle crew went up and physically replaced hardware. The International Space Station has lost several of its control moment gyros over the years too, each failure a big deal for operations. These platforms were designed for decades, not 100 years, and they still needed human servicing. Your Starship does not get shuttle visits. If a gyro dies, it stays dead, unless you can rebuild or replace it with what you carried at launch or can manufacture inside the ship. So you get this slow squeeze. More reaction wheels and CMGs fail or get noisy. More Star Tracker pixels die. More gyro drift has to be corrected in software. Control is still possible, but it becomes rougher, more fuel-hungry, and more sensitive to small errors. The first true failure in attitude control is not your ship tumbling wildly. It comes much earlier, when you start to lose fine pointing. High-gain radio antennas, and especially laser communication systems, have very narrow beams, with divergences measured in microradians. Over a distance of a few light years, a 1 microradian beam spreads out to tens of millions of kilometers. But even then, your pointing has to be accurate enough that Earth or a relay receiver stays inside that cone. If your attitude knowledge is off by a few microradians because of sensor noise and aging gyros, half your beam can miss. Your data rate drops, your link becomes marginal. You start scheduling long, slow, heavily error-corrected contact windows instead of routine communications. The same thing happens with navigation burns. A small rotation error before a course correction means your delta V goes partly in the wrong direction. You correct that with another burn, then another. Each correction costs propellant. Over decades, that waste shrinks what is left for critical maneuvers near the target system. By the time attitude control is broken in the way that really matters, the ship can technically still rotate. Wheels can spin, thrusters can fire, gyros still output numbers. But you have lost the ability to point with the precision the mission needs. Every maneuver is sloppy, every communication link is borderline. You are spending more fuel and more computer time fighting your own degraded hardware, just to keep the nose and the antenna roughly where they should be. And all of this constant trimming, spinning, wheel running, and thruster firing is drawing power from systems that also have to last a full century, systems whose own output is already starting to sag long before you reach the target star. You know you are in trouble when your Starship still has engines, still has propellant, but you are arguing about whether you can afford to turn the lights on and fire a thruster in the same hour. That is what power systems look like on a 100-year mission. They do not fail as a clean on or off. They fail by squeezing every margin until nothing is comfortable anymore. Start with the most basic source, sunlight. Near Earth, at 1 astronomical unit from the sun, the solar flux is about 1,360 watts per square meter. A good solar panel today might turn 20 to 30% of that into electricity, so a square meter could give you a couple of hundred watts, like a bright desk lamp or a small microwave. That is great for satellites in Earth orbit. But your Starship is not staying near one sun. As soon as you move away, the intensity drops with the square of the distance. At 10 astronomical units, 10 times farther than Earth, you now get only about 1% of the original sunlight per square meter. At 100 astronomical units, around the scale of the outer Oort cloud, it is about 1/100th of 1%. For a mission going between stars, there is a long stretch where solar panels are almost useless. You would need absurdly huge areas of panel to get any meaningful power in the deep interstellar void. That is why we put radioisotope power sources on Voyager and similar probes. Solar simply does not scale for multi-light-year cruises. On a Sentry ship, panels might still be useful near the departure star, maybe for early acceleration or initial operations, and again near the destination star. But for the main cruise, your real power budget comes from nuclear sources, not from sunlight. Even before you leave the home system, solar arrays have another long-term problem. They age. In Earth orbit, panels lose roughly 0.5% to 1% of output per year due to radiation damage, micrometeoroid hits, and thermal fatigue. After 30 years, that could leave you at around 75% of your original power, even if you stayed at the same distance from the sun. Stretch that curve out over 100 years, and you are looking at well over half your power gone, just from panel degradation. Now combine that with the distance loss, and you see why no one should bet the entire ship on sunlight. Yes, you can replace panels, but only if you launch that extra mass, or can manufacture them on board. That means mining raw materials, refining silicon, making high-purity cells, and assembling large structures in zero-G. It is possible in theory, but every step is another system that has to work flawlessly for decades. So the logical answer is nuclear. A Sentry Starship almost certainly carries one or more reactors. A small fission reactor in the kilowatt to megawatt range can produce stable power day and night. independent of distance from any star. But reactors are not timeless either. Inside a reactor core, fuel atoms split, releasing energy, but also throwing off neutrons that slam into surrounding materials. Over years, those neutrons make the fuel and the structural metals brittle. They change the crystal structure. They cause swelling. They create gas bubbles inside solids. On Earth, commercial reactors are usually licensed for about 40 years, sometimes extended to 60 or 80 with heavy inspections and component replacements. The pressure vessel, the thick metal shell that holds the core, is one of the most life-limited parts, and it is not easy to swap. Your Starship reactor has to run for something like 100 years, with no option to replace that pressure vessel. You can run it at lower power to reduce damage. You can use advanced fuels and clever core designs to spread out the neutron dose. But you cannot escape the basic physics. Over time, embrittlement grows. Welds and supports inside the core see increasing stress. Control rods and mechanisms age. The team in year 70 will be managing a machine whose exact material state is outside the envelope of any Earth-based testing. On top of that, you probably have smaller nuclear sources like RTGs, radioisotope, thermoelectric generators. These are solid-state devices with no moving parts. They generate power from the heat of radioactive decay, often using plutonium-238. That isotope has a half-life of about 87.7 years. So, after one half-life, one chunk of fuel gives off half as much heat as at launch. After 100 years, you are down to roughly 40 to 50% of the original thermal power. The thermocouples that convert that heat into electricity also degrade, so the electrical output drops even faster. RTGs are very reliable for decades, but they are not magic forever boxes. On a 100-year ship, your backup RTG power is fading all the time. Now add the shortest-lived elements in the power chain, the actual energy storage devices, batteries, and capacitors. Batteries are necessary because your loads are not constant. Sometimes you need a surge for a big burn or a high-power communication, and you cannot size your reactor just to cover peaks. That would be too heavy. So you charge batteries during calm periods and dump that energy during spikes. But every time you charge and discharge, the electrodes and electrolytes change a bit. Even the best space-qualified batteries today lose capacity over years. Retaining 70 to 80% capacity after a decade is considered very good performance. Over 50 years, without replacement or reconditioning, any chemically based storage system turns into a weak, unreliable remnant of what it was. Over a century, it is basically dead weight unless you can refurbish or rebuild it. Capacitors, supercapacitors, flywheels all have their own aging issues. Dielectric materials break down, bearings wear, containment shells fatigue. So on a Sentry ship, you have to treat every battery and every storage device as a short-term buffer. The real long-term source must be something like a reactor, or RTG. Anything based on chemistry has a limited clock, unless you keep refreshing the active material. When you combine these realities, you see why the first real power failure on a 100-year Starship is not a sudden blackout, but a slow collapse of flexibility. At the start of Mufimemut, you have margin. The reactor runs at half its maximum. The RTGs are fresh. The batteries can take large charge and discharge cycles. You can run life support, spin the habitat, fire ion thrusters, and point a high-gain laser at home, sometimes even at the same time. Decades later, everything is tighter. The reactor team has limited how hard they run the core to preserve it. The RTGs are giving out maybe half their original power. Some battery packs are retired because their internal resistance is too high. They heat up too much under load. Others are derated, only allowed to use a fraction of their designed capacity. Your total available continuous power might still be enough for basic life support and slow cruise, but you no longer have generous peak capacity. So the first thing that fails in the power system is the ability to handle spikes. You cannot just decide, on short notice, to send a massive burst of data to Earth using a high-power transmitter, while also running a big maneuver and a heavy science campaign. You start planning around power the way submarines plan around air and stealth. No big burns during the major comm windows. No high-gain transmission when life support is cycling heaters and pumps. Non-critical systems are shut down entirely during maneuvers. By year 70 or 80, a lot of your operational rules are built around these constraints. Maybe certain labs only power up once a week. Maybe large-scale attitude changes are scheduled months in advance, to be done when the reactor is sitting in its most stable configuration. Any unplanned emergency load, like a pump switching to a backup mode, or a faulty heater staying stuck on, can push you over a line where voltage droops, some boxes reset, and your already stressed electronics and control systems take another hit. And remember, all the heat wasted from this power, all the inefficiency, has to go somewhere. You cannot just dump it into air like on Earth. You must radiate it away into space, using large, delicate panels that are themselves vulnerable over a century. So when power gets harder to supply and more precious to use, the consequences feed directly into the next critical system. The only thing standing between your habitat and a slow bake or a deep freeze: the ship's thermal control network. How do you keep a starship from slowly cooking itself when the only way to dump heat is through huge, fragile wings that space keeps trying to tear apart? In space, getting heat out is harder than getting power in. There is no air to carry heat away, no wind, no convection. You get rid of waste heat mainly by radiation, by glowing in infrared. That is why a ship running megawatts of power needs radiators with areas in the hundreds to thousands of square meters, thousands to tens of thousands of square feet. These are big, thin structures, full of coolant channels or heat pipes, spread out to see as much cold, deep space as possible. But thin and spread out also means vulnerable. A micrometeoroid, or a piece of interstellar dust that would just pit the main hull, can be a serious problem when it hits a narrow coolant tube. One good hit can punch a pinhole, or tear a whole section, and your working fluid starts to leak out, drop by drop. You might not see a dramatic spray. You just notice that over months the pressure in one loop is falling, and the temperature of one part of the ship is creeping up. Over decades, a handful of these small leaks can silently remove entire sections of radiator from service. The total area shrinking by 10 or 20% might not sound huge until you realize that now your core and your electronics are running hotter all the time. To move heat from where it is made, inside the ship, out to those radiators, you rely on two main tools: heat pipes and pumps. Heat pipes are sealed tubes partly filled with a working fluid. One end is hot. The fluid evaporates there, flows as vapor to the cold end, condenses, and a wick pulls the liquid back. They are passive, reliable, and can last for decades, but not forever. Every cycle is a phase change and a flow. Tiny impurities can separate out. Microleaks can slowly let gas in or working fluid out. Repeated freeze-thaw cycles or radiation damage can change the wick or the wetting behaviour of the fluid. Over 50 or 100 years, some fraction of your heat pipes will dry out or partially fail, turning into simple metal rods with far less heat-moving power. Mechanical pumps handle the rest. On the International Space Station, large pumps push ammonia or other fluids through external loops, and those pumps have already needed maintenance and replacement on timescales of years, not decades. Bearings wear, seals age, motors degrade. On a 100-year Starship, every pump you launch has to either be rebuilt in place, swapped for a spare, or replaced with a new one manufactured on board. That is not just a pump, that is every associated valve, sensor, gasket, and motor controller. A single sticky check valve in a cooling loop can starve one radiator panel, forcing the rest of the system to run hotter to compensate. Even if all the plumbing stays intact, the radiator surfaces themselves change. The key number here is emissivity, a measure of how well a surface radiates heat as infrared. Thermal engineers choose coatings that have high emissivity in infrared, so they radiate well, and low absorption in visible light, so they do not soak up too much starlight. That perfect balance does not last. Near stars, ultraviolet light and atomic oxygen chew at surfaces. Further out, Constant micrometeoroid hits roughen and pockmark them. Chemical reactions in the coating layer continue slowly. Over a decade, maybe our emissivity drops a couple of percent, or the reflectivity in sunlight changes a bit. That sounds minor when you just look at one number on a spec sheet. But 50 years into the mission, those small percentage changes stack. A panel that used to run happily at, say, 250 Kelvin might now sit at 270 or 280 Kelvin under the same heat load. In Celsius, that is a jump of 20 or 30 degrees. The radiators are doing less work, so the coolant returning to the ship is warmer, and every component tied into that loop runs hotter than the original design assumed. We already see how sensitive spacecraft are to this, even on short timescales. Many satellite mystery failures boil down to thermal issues. A battery that spends too many orbits at slightly higher temperature starts to lose capacity fast. An instrument that was carefully calibrated at one temperature drifts out of spec when its internal electronics heat up by a few degrees. Some missions have instruments that must be turned off during certain parts of their orbit, just to avoid overheating. Those are systems built for lifetimes of years, with frequent communication and a chance to adjust operations. On a Sentry ship, the internal heat profile is not even constant. Early on, you might have heavy propulsion use, running big engines and charging large batteries. Later during cruise, propulsion power drops, but life support and computing might grow as the population and software load change. Labs might be added, habitats reconfigured, new equipment built on board. All that changes where heat is generated, and how much. Your original thermal design was built around conditions in year 0. By year 50, the ship may have a completely different pattern of hot and cool zones, but you still have the same aging radiators, the same plumbing layout, the same core geometry. So what really fails first in thermal control? It is not an instant boil or freeze. It is the gradual push of every component outside its comfortable temperature window. Most electronics, for example, are rated to operate best in a certain band, often something like 0 to 40 degrees Celsius for comfortable gear, wider for hardened space hardware. If a processor that used to idle at 30 degrees spends its life at 40 or 45 instead, you may think, that is still within spec, no big deal. But higher temperature accelerates almost every failure mechanism. There is a common rule of thumb in reliability engineering. Many chemical and diffusion-driven processes double their rate for every 10 degrees Celsius increase. That means if a given failure mode would take 30 years, at one temperature, bump that temperature by 10 degrees, and you are down to around 15 years. Bump it another 10 degrees, maybe you are down to 7 or 8 years. On a 100-year Starship, that compounding is brutal. By year 60, you may find that parts of the ship that were supposed to have comfortable margins are now running just a bit hot, and as a result, boards and modules that should have lasted 30 or 40 years are burning out in 5 or 10. Sensors drift faster. Plastic insulators harden and crack. Solder joints creep. Capacitors dry out. All because the radiators lost a bit of area, or their coating performance shifted, or a few heat pipes quietly died, and nobody noticed until the average temperature in that section rose by 10 or 15 degrees. The crew sees it as a rise in nuisance problems first, a power converter that trips offline more often in the hot half of the orbit around the ship's spin, a science instrument that fails self-check on days when several other loads are running, a cluster of computers in one module logging more errors than an identical cluster mounted near a different radiator loop. Thermal maps showed those zones are a little warmer, but not enough to scream failure on their own. You could fix it by adding new radiator panels or re-plumbing loops, but that costs mass, fabrication time, and crew effort, all while other systems are also demanding repairs. In the end, the deepest danger of thermal control problems is that they accelerate every other failure on the ship, especially in electronics. A slightly hotter processor is more sensitive to radiation hits. A warmer memory module sees more leakage, making bit flips more common. A control board sitting next to an aging pump motor runs near its maximum rating all the time, cutting its lifetime in half. So as your radiators age, your pipes leak, and your coatings drift, you are not just fighting temperature, you are watching the entire nervous system of the ship. All the sensors and computers and communication links slide down a steeper reliability curve than you budgeted for. And that leads straight into the next weak spot. The part of the ship that cannot hide behind armor or better plumbing. The electronics and software. The part that has to stay logically sharp while the hardware underneath it is literally being cooked and irradiated for a full century. How long can you trust a computer that has literally been under fire every second for 100 years? From the moment your Starship leaves Earth's magnetic shield, every memory chip and processor on board sits in a constant shower of high-energy particles. Each of those particles can flip a bit in memory or logic. A single event upset. On modern spacecraft, engineers expect multiple of these flips per day, even with shielding. So from day one, your computers are living with random errors. The first line of defense is error-correcting codes in memory. You store extra bits so the system can detect and fix single-bit flips, sometimes even double-bit errors. For really critical logic, you can use triple modular redundancy, 3 copies of the same circuit running in parallel, and a voter circuit picks the majority answer. If one copy is hit, the other 2 outvote it. This works well for a while, but a 100-year mission is not a while. Over decades, radiation does more than flip bits temporarily. It slowly changes the hardware. Transistors inside chips build up trapped charge and physical damage. Some memory cells stop holding charge properly, so they behave like they are permanently 1 or permanently 0. Logic gates develop stuck outputs. At that point, error-correcting codes are no longer just cleaning up occasional noise. They are masking around permanent holes in the memory map. Spare rows and columns can be mapped in, bad areas can be fenced off, but your pool of good hardware shrinks year by year. At the same time, the analog parts around the digital cores are drifting. These are the pieces most people forget. The resistors that set gain, the capacitors that smooth signals, the crystal oscillators that define system time. Resistors change value slowly as materials age. Capacitors, especially ones with liquid electrolytes, dry out or leak. Their ability to hold charge drops, and their internal resistance rises so circuits run hotter and less stable. Oscillators, which might start life at 10 MHz with parts per million accuracy, wander as their crystals age. As solder joints creep, as packaging stress relaxes, a tiny frequency error may not matter for one chip, but across a whole network of synchronous systems, it can shift timing margins and push communication links out of their sweet spot. Everything that depends on precise voltages and timings starts to drift. Analog to digital converters no longer map input signals to the same digital numbers they did in year 5. Digital to analog converters, driving thrusters or radio front ends produce slightly different outputs for the same command word. The phase-locked loops in radio equipment need more frequent retuning. The standard solution is calibration. You build tables that say, when this sensor reads X, the real value is Y, and you update those tables as you measure the drift. For a while, that works very well. The software learns the new behavior of the hardware and corrects for it. But the tables were designed with some expected range in mind. If a reference voltage drifts far enough, or an oscillator wanders too much, you end up outside the range the software knows how to fix. Now your calibration code is extrapolating, making guesses in a space it was not written for. That is where subtle, mission-scale errors creep in. While all of this physical aging is happening, the code that runs on top of it is changing too, and not always in clean, controlled ways. A 100-year mission means the original flight software team is gone long before the ship arrives. Generations of programmers and maintainers inherit the code. They patch bugs, add features, change operating modes, bolt on new safety checks. Over time, the code base grows layers. A quick workaround here, a temporary bypass there, an emergency override that never got fully removed after the crisis passed. Documentation drifts out of sync with reality. People become afraid to touch certain old modules because no one fully understands what else depends on them. Change in one part of the system can have odd side effects somewhere completely different because of assumptions baked in 60 or 70 years earlier. We already see this pattern in long-lived systems on Earth. Air traffic control software, nuclear plant control systems, and some military platforms run code that is decades old, with patch on top of patch. These systems are expensive to modify, risky to upgrade, and sometimes behave in ways that only a handful of experts still fully grasp. Now take that situation. put it on a ship many light years from any support, and ask it to stay safe and correct under constant radiation. You do not get to shut down the Starship for a full refit. It has to keep running while you operate on it. The combined effect is not a clean crash, it is a slow erosion of trust. Early in the mission, a computer reset is a rare event, a serious anomaly that gets a detailed post-mortem. Bit flips are logged and corrected quietly in the background. Data from sensors and navigation systems lines up cleanly with models. People are happy to let the autopilot handle almost everything. By mid-mission, resets are more common. Once every few months, then once a month, then once a week. A node somewhere in the ship's network reboots. Sometimes you can trace it to a radiation event. Sometimes it is a software race condition that only shows up under weird timing, after enough drift in hardware and enough patches in the code. Navigation solutions show occasional jumps, then settle back after recalculation. Science instruments show sporadic bad readings that need to be thrown out. Each time that happens, crew confidence takes a small hit. Maybe the hardware is failing faster than expected. Maybe some of the legacy code has a landmine nobody fully understands. The engineers respond by adding more checks, more watchdog timers, more conservative limits. That makes the system safer in one sense, but also more brittle and complicated. By year 60 or 70, the main job of your software team is no longer add new features. It is do not break the few paths that still work. Every proposed change has to be weighed against the risk of triggering some hidden interaction in a corner of the system no one has touched for 40 years. Some bugs become known issues that everyone learns to live with because fixing them might disturb too many other dependencies. At that point, the computers are still running. The network is still passing messages. But from a human point of view, the first real failure in electronics and software has already happened. It is the loss of clean, simple trust. When a display shows a strange value, your first thought is not the sensor saw something new, it is this another glitch? When an automatic safety routine triggers, you wonder whether it is reacting to a real fault, or a stuck bit in some deep control path. And this is where the tension really spikes, because the next systems in the chain, the life support loops that move water, air and waste, depend on those same aging sensors and that same patchwork software. If you cannot fully trust the numbers coming out of your electronics, how do you safely run the pumps and filters that stand between your crew and suffocation? You can survive a bad sensor in an engine, but what happens when the sensor that lies to you is the one that says how much oxygen you have left? Life support hardware is where all the abstract risks turn into a direct threat to breathing, drinking, and staying conscious. On the International Space Station, the Environmental Control and Life Support System, ECLSS, already does a lot of what a Starship needs. It recovers more than 90% of water from air humidity and urine, and it recycles a large fraction of oxygen. But it does this with a constant stream of maintenance, replacement parts and support from Earth. Pumps clog, filters saturate, valves stick, CO2 scrubbers hit capacity, and their cartridges have to be swapped. ISS hardware was never designed to sit for 100 years and just work. It is modular, trucked up a piece at a time, repaired or upgraded with every cargo mission. On a 100-year Starship, you do not have that luxury. You still have the same basic functions to do. You must pull CO2 out of the air. You must keep oxygen at safe partial pressure. You must keep humidity in check, recycle almost every drop of water, and handle waste streams from hundreds or thousands of people. And you have to do it with hardware that you either brought at launch or can fabricate in your own workshops. Take CO2 scrubbing. Many systems use solid amines or lithium hydroxide to bind carbon dioxide from air. Disposable lithium hydroxide cartridges were used on Apollo. Once saturated, they are done. That is not acceptable on a Sentry ship. You would drown in spent cartridges, so you move to regenerable systems. There you bind CO2 at one set of conditions, then later drive it off by heating or lowering pressure, so the sorbent can be used again. It looks like a closed loop. The problem is that the sorbent materials do not stay perfect. Over thousands of cycles, the pores where CO2 molecules attach can clog with contaminants. The granules can crack and break down into dust, changing how gas flows through the bed. Trace compounds in the air, like volatile organics from humans and plastics, can bind to the sorbent and never fully come off. That slowly eats away at the effective capacity. 10 years in, the system still works. But you need longer regeneration times or higher temperatures. 30 or 40 years in, a bed that used to handle a certain flow now needs to be twice as big, or swapped out more often. If you did not plan for that degradation, you end up with a creeping CO2 problem. Not a sudden spike, but a slow rise in baseline levels. People get headaches more often, sleep quality drops, cognitive performance falls a bit. The hardware looks up on the status page, but it is silently undersized for the aging sorbent. To stay safe, you either bring huge mass in the spare sorbents, or you build full chemical reprocessing lines on board to regenerate and rebuild sorbent materials from scratch. That is a full industrial process, running in a closed environment. Then there is water. Any system that moves water, stores it, filters it, or vaporizes it, becomes home to microbes. On ISS, biofilms have already been found inside water systems, and even inside pipes, not just on exposed surfaces. A biofilm is a slimy layer of bacteria and other microbes stuck to a surface. They protect themselves with secreted polymers, they trap nutrients, and they can be very hard to kill completely. In a starship's plumbing, biofilms do 3 dangerous things. They clog filters, so pressure drops and flow slows down. They corrode metals, because their byproducts can be acidic or otherwise reactive, especially at tiny scale, and they generate their own chemicals, some harmless, some smelly, some directly toxic. You can run sterilization cycles with heat, UV, or chemicals, but you will never get everything. Over decades, some microbial communities will adapt. They may learn to tolerate your cleaning methods, or hide in low-flow corners of the system until the next calm period. Pipes slowly narrow, filter change intervals shorten, odd tastes or smells appear in certain lines. You can respond by building more redundancy into the network, more bypass lines, more spare filters. But every added part is more surface area for microbes. The only real defense is continuous, high-level maintenance. And that is exactly the thing that gets harder as hardware ages and spare parts run low. Spare parts are the other brutal limit. Suppose a key pump in a 20-ton life support module is rated for 20 years of continuous operation. A naive plan says, we will bring 4 spares that covers 100 years, but that assumes perfect conditions. It assumes every pump hits its rated life. It assumes you never have a manufacturing defect, never get a bad batch of bearings, never see a line of pumps all fail early, because they shared the same subtle design flaw. It also assumes the spares sit on a shelf for decades without aging. Real materials do not pause aging just because you have not turned them on. Rubber gaskets harden in sealed bags. Plastic hoses slowly outgas and become brittle. Lubricants separate or react over time. Electronics sitting in storage still see background radiation, still see small temperature shifts, still suffer from slow chemical changes. A pump pulled from storage in year 60 might not behave like a fresh pump from year 0, even if it has 0 hours of runtime. And behind each big hero component, like that pump, is a network of small, cheap parts that are often harder to replace. Flow sensors, pressure switches, oxygen, partial pressure sensors, tiny check valves with plastic seats, well-balanced fans that keep cabin air mixed so you do not get CO2 pooling in corners. If a fan motor fails, maybe you can rebuild it. If its specially profiled blades warp or crack, you need to manufacture new ones with tight tolerances, or you get noise, vibration, and poor airflow. This is why the first real failures in life support are almost never dramatic blowouts. They start subtle. 1 week, the oxygen level trends a little low during heavy exercise periods. A CO2 alarm that used to never trigger during sleep now chirps occasionally in one section of the ship. Humidity creeps up in the agricultural ring because a dehumidifier coil is slightly fouled and its sensor underreads. You chase these problems with calibration first because your electronics team knows sensors drift. But if you adjust too aggressively in software, you can end up telling yourself the air is fine when it is not. On the other hand, if you mistrust every sensor and build in huge safety margins, you might waste power and sorbent capacity, running scrubbers and pumps harder than needed, which shortens their lives. Over time, the maintenance load climbs. More filters to change each month, more hours spent flushing lines, bleaching tanks, scrubbing biofilms mechanically, more time spent cross-checking multiple independent sensors to decide which one is lying. Crew who should be doing science or training spend a bigger fraction of their lives just keeping water and air systems limping along. At some point, the mission's bottleneck is not your ability to reach the target star. It is your ability to keep a complex, aging, microbe-filled, patch-repaired industrial water and air plant running without a break for a century. The big fancy hardware, like Sabatier reactors or oxygen generators, might still have plenty of theoretical life left, but a $30 pressure transducer deep inside the system goes out of spec, and suddenly a whole loop cannot be trusted. And remember, all this hardware is trying to support not just pipes and tanks, but a living, evolving biological system on top of it, your closed farms and ecologies. If the machinery that feeds and ventilates that biosphere starts to falter, how stable can the living part of the ship really stay over decades, when plants, microbes and insects have their own ideas about how to grow and spread? Plants, microbes and insects do not care about your mission plan. They will follow their own rules, and over 100 years those rules shift in ways you cannot fully predict. We already know that plants in space do not behave exactly like on Earth. On the ISS, crews have grown lettuce, wheat, flowers, small test crops. They grow, they make edible leaves and seeds, but the details are different. Roots do not know which way down is, so they spread strangely. Water does not flow the same way in microgravity. It sticks to surfaces. It forms blobs, so some roots drown while others dry out. Microbes around the roots, on leaves and in nutrient solutions organize themselves differently. Some strains that are minor players on Earth take over in space. Some that are important on Earth barely hang on. On your Starship, your hydroponic trays, soil beds, algae tanks and fish ponds are not just farming equipment, they are full ecosystems. After 10 years, the microbes in one hydroponic line will not match the microbes in another, even if you started them the same way. After 50 or 100 years, those ecosystems have had time to drift, adapt and evolve in response to your lighting cycles, your nutrient recipes, your cleaning procedures, and your small leaks and accidents. A fungus that tolerated low light might become more aggressive under your LED spectrum. A bacteria that clung to the inside of one tank fitting might become an important nitrogen recycler you never planned for. The goal of a closed ecology is to keep key nutrient loops tight. You want nitrogen to cycle from waste to bacteria, to plants, to food and back. You want phosphorus, potassium, carbon, and trace elements all following reliable paths. The problem is no loop is perfectly closed or perfectly balanced. There are always small asymmetries, tiny losses of nitrogen as gas leaks, trace metals concentrating in one compartment, organic residues building up in corners where flow is slow. On Earth, when a river carries extra nutrients downstream, a wetland or an ocean absorbs them. When a forest builds up certain toxins, wind and rain spread them out. There is always a downstream for the system to dump excesses into. On a Starship, there is no downstream. If a trace contaminant, say a heavy metal from corrosion or a specific plasticizer from your materials, slowly accumulates in the water and soil, it has nowhere to escape except your filters and your processes. Miss that build-up and it can start to hit plants or animals at levels that change growth or health. Over decades, nutrient imbalances can show up in strange ways. One year, your main grain crop yields slightly less, and you cannot match it to obvious stress. The next decade, you discover that a key micronutrient has been binding to something in your soil, slowly becoming less available, while another element has been building up to levels that stress root systems. Your models from year 0 no longer match the reality in year 60 because the chemistry inside your closed system has quietly drifted. Biodiversity is another hard constraint. You cannot bring a whole rainforest. You probably start with a few dozen plant species, some staple grains, some fast vegetables, maybe some legumes for nitrogen fixation, some fruit trees for long-term yield. You add a few fish or insect species for protein and for ecosystem services, pollinators, decomposers, and you bring microbiome starters for soil and water. That selection is a massive bottleneck. You have compressed the planet's biodiversity, millions of species, into maybe a few hundred at most inside the ship. Now add time. Over 100 years, that is many generations for plants, thousands of generations for microbes and insects. Genetic drift, selection, and random mutations all shape the population. In one herb bed, a particular aphid strain might learn to exploit your favourite salad plant much more efficiently than its cousins. In a fish tank, a strain of algae that tolerates slightly higher CO2 might overgrow its competitors, turning clear water into recurring blooms. On the other side, a helpful symbiont bacterium in the soil might lose a key function or be outcompeted, and suddenly a plant that relied on it for phosphorus uptake becomes finicky, more likely to suffer deficiencies. Because your starting gene pool is narrow, each change matters more. A pest that becomes super fit has few natural enemies. A symbiont that goes extinct in your system has no easy replacement. Unless you planned and stored backups and know exactly how to reintroduce them, the biosphere on the ship in year 80 is not the one you launched. It is a related but distinct ecosystem, with its own balance of winners and losers. We already got a taste of how hard closed ecologies are, even without radiation, interstellar travel, and multiple generations of crew. In the early 1990s, the Biosphere 2 project in Arizona tried to keep 8 people alive in a sealed environment for 2 years. The dome included forest, ocean, desert, and farm zones. It was designed with careful models, yet once sealed, the oxygen level dropped over time, CO2 levels swung up and down, and unexpected chemical reactions in the concrete structure soaked up oxygen. Some animals and pollinators died out. Ants and cockroaches surged. The team had to adjust operations and eventually bring in outside air. That was in a huge structure, with Earth gravity, stable sunlight, and constant access to external analysis and support. 2 years, and it still ran into serious surprises. A 100-year Starship asks for much more. Different gravity, artificial light, tight mass budgets, constant radiation, and no outside resupply. Even if you start with far better knowledge and technology than Biosphere 2 had, you are still asking your onboard ecosystem to survive, adapt, and keep feeding and oxygenating people for 5 human generations or more. So what actually fails first in closed ecologies? It is not that the farm just collapses overnight. The first thing you lose is predictability. In the early decades, you can say, this area of hydroponics will give us this many kilograms of food per month. These algae reactors will give this much oxygen. These waste processors will return this much nitrogen. Your planning is tight. Charts and spreadsheets match reality within a few percent. Later, you start to see more surprises. A key crop that was reliable for 30 years suddenly gets hit by a fungus that found a new way to attack it under your light and humidity cycles. Yields drop by 30% for that crop in a single year. A bacterial community in a root bed shifts, nitrogen fixation slows, and you are forced to import nitrogen from reserves, or cut back planting until you can rebalance the microbes. An algae strain you introduced for high oxygen output escapes its tank environment, seeds other systems, and causes recurrent blooms that choke filters and demand unplanned cleanouts. Planning food and oxygen goes from being a strong, confident forecast to being a set of probabilities. There is a 90% chance we hit this yield, 10% we come in low. You keep larger safety margins in stored food and stored oxygen, which means more mass devoted to buffers, less to other mission goals. You spend more crew time on monitoring pests, adjusting nutrient mixes, pruning back species that are overgrowing, reintroducing ones that are fading. That unpredictability bleeds into psychology too. Farmers on Earth deal with weather and pests, but they have neighbours, markets, and global trade behind them. Your ship does not. A single season of bad yields is not just an economic hit, it is a direct threat to survival. The crew learns to live with that risk, but it adds another layer of stress and another way for the mission's safety margins to erode. And remember, all of this biological action sits on top of the physical life support hardware and the ship's structure. Leaks from a nutrient tank change the whole water balance. A small contaminant escaping from a manufacturing process might enter the food chain. Off-gassing from new materials in a habitat can end up feeding or poisoning microbes in your farms. The line between closed ecology and ship atmosphere and water system is thin, so if the living part of your ship is already this sensitive, evolving in ways you can only partially control, what happens when you zoom in one level further, to the actual air and water in every cabin, and the slow, hard-to-see shifts in chemistry that add up over a century? You can patch a crack in the hull, But how do you patch a slow change in the very air and water that everyone is built on, when that change is spread over an entire ship and an entire century? Start with leaks. No pressure vessel is perfect, especially when it is big, full of hatches, viewports, ports, and miles of joints. The ISS has seen leak rates of fractions of a kilogram of air per day at times, that is a few hundred grams, about the mass of a can of soda, slowly drifting away into space every 24 hours. Crews find and fix those leaks because they can watch tank levels, they can listen for hissing, they can do pressure tests. On a 100-year Starship, even a much smaller leak rate adds up. Say you manage to get your total leak rate down to just 5 grams of air per day across the whole ship, less than a teaspoon of water by mass. Over 1 year, that is about 1.8 kilograms. Over 100 years, that is 180 kilograms, about 400 pounds, of atmosphere gone. If the leak rate is 10 times higher, still small by ISS standards, now you are at nearly 2 tons of air lost in a century. You cannot ignore that. Replenishing lost air means splitting water into hydrogen and oxygen, cracking it with electrolysis, or pulling oxygen back out of CO2 with chemical loops. That costs power, hardware life, and water. Urine and humidity recycling give you some water back, but not 100%. If you are really bold, you might plan to gather volatiles from comets or icy bodies in the departure system or the target system, but during the deep space cruise, there is nothing to grab. Every gram that leaks is a tax on your limited water reserves and your power budget. While you are fighting to keep the total amount of air and water in range, its composition is quietly changing. Humans do not just exhale CO2 and water, they breathe out acetone, isoprene, ammonia, and many other volatile organic compounds. Skin, hair, and clothes shed particles. Every plastic panel and cable releases tiny amounts of plasticizers like phthalates. Adhesives, sealants, floorings, foams, all outgas small molecules, especially when new, but some keep outgassing for years. Cleaning products, paints, and fire retardants add their own chemicals. On ISS, trace contaminant control systems use activated charcoal beds and catalytic oxidizers to grab and break down many of these compounds. Filters capture particles. Catalysts burn off organics to CO2 and water. That works well over mission lengths of years, but on a Starship that runs for a century, the list of compounds never gets shorter. It only grows. Every time you introduce a new material, a new cleaning agent, a new sealant for repair, you add one more source. If a filter is slightly less effective for one rare compound, that compound might slowly climb. Maybe it is a solvent vapor from a plastic, maybe a byproduct from a certain bacteria in the life support system. At levels too low to trigger alarms, it can still interact chemically with other things, clogging sorbents, changing how CO2 scrubbers behave, or irritating human lungs subtly. You might see more people with mild headaches, sleep issues, or allergies in one area of the ship, and not immediately connect it to a trace gas that was never on the original spec sheet. Now look at water. Modern systems on Earth and on ISS can recover 90 to 95% of water from humidity, urine, and other waste. That sounds impressive, but flip it around. If you lose 5% per cycle, and your crew is 1,000 people, each using maybe 50 to 100 litres per day of total water flow counting drinking, washing, and system processes, even small percentage losses translate into large absolute numbers over time. You start with a huge initial reservoir, hundreds to thousands of tons of water, simply to make the math work over a century. Membranes in reverse osmosis units foul. Filters clog. Biofilms grow in low-flow corners. Scaling from minerals forms on heat exchangers and heater elements. Every few years, you're pulling out modules, chemically cleaning them, or replacing them entirely. Over decades, you might have to redesign whole parts of the recycling chain because the original membranes are no longer manufactured on board, or the original materials have degraded. That means building new chemistry with whatever polymers and catalysts your ship's industry can actually produce, which might not be exactly what the launch designers used. Each redesign risks new side effects on water taste, trace content, or compatibility with crops and microbes. And then there is fire. A single serious fire event on board, even if contained quickly, can dump a cocktail of combustion products into the air. Soot, carbon monoxide, nitrogen oxides, And if plastics or halogenated materials burn, gases like hydrogen chloride or hydrogen fluoride. On Earth, once the fire is out, you ventilate. Fans push smoke outside, and over time, wind and weather dilute and remove toxins. You can rip out burned surfaces and rebuild. On a Starship, you cannot vent to the outside casually. Dumping air to space is a last resort, so you rely on scrubbers and filters to clean up the mess. That means for a while your filters are hit with a much higher load than usual. Some of the residues find their way deep into ducts, corners and filter media, where they may never be fully removed. They can keep outgassing back into the airstream at low levels for years. Airflow patterns themselves can change. If soot or sticky residues build up in certain ducts and half-block them, over time, that alters how fresh air reaches different cabins and how quickly CO2 and trace gases are pulled back to scrubbers. All of this adds up to a complex, slowly changing chemical environment that no one person fully holds in their head. The first real failures in atmosphere and water are not alarms screaming toxic or no oxygen. They are the unknown unknowns creeping in. Maybe a specific wall panel adhesive, used heavily during a refit in year 20, releases a compound at very low rates. The original team tested it for a few years and saw no issue. But over decades, that compound binds strongly to a part of the CO2 scrubber sorbent, permanently occupying some of its capacity. The scrubbers keep working, but their effective life between regenerations gets shorter and shorter. No one remembers the adhesive test report from year 20. All the crew in year 70 see is that they are going through scrubber cartridges faster, and that their models of CO2 removal no longer match reality. Or a cleaning fluid used in one part of the ship leaves behind residues that slowly dissolve into the grey water system. That changes the chemistry in a particular treatment tank, giving an edge to a microbial community that produces more of a certain byproduct. That byproduct evaporates a little, reaching the air, and reacts with another trace gas to form something irritating. The first signs are weird smells, unexplained headaches in one area, and slight increases in how often certain filters need replacement. None of that looks like a single dramatic failure, but it erodes margins and trust. The crew starts to add more and more "do not use this material near that system" rules. They tighten limits on exposure to new polymers, solvents and cleaners. Every repair requires checking a database of chemical compatibility, trying not to create a new long-term interaction. The ship's atmosphere and water are still within broad safety limits, but the effort to keep them there grows. And the complexity of the hidden chemistry under everyone's daily life gets harder to manage. And remember, all of this is happening in a habitat where gravity, air circulation, and human biology are already under stress. The next layer of risk is built directly on that: the ship's artificial gravity itself, the constant spin and tension that bones, muscles, and structures are relying on, and that also has to hold up under 100 years of motion and impacts. You trust that floor under your feet more than any readout. But on a Starship, even down is a machine that can wear out. To give you anything like 1G on a long mission, you do not want to live in 0G and hope exercise fixes everything. You spin. A common design is a big ring, maybe 500 meters in radius, about 1,640 feet. Spin it at around 1 rotation per minute, and the outward pull feels roughly like Earth gravity for people standing on the inside surface. At that rate, the structure itself is moving at about 50 meters per second, roughly 110 miles per hour, in a circle, all day, every day. Every single rotation is a stress cycle. The ring wants to fly apart, the spokes and joints hold it together. The metal stretches a tiny bit, then relaxes over and over. Run the numbers for 100 years. 1 rotation per minute means 60 per hour, more than 1,400 per day, over 500,000 per year, tens of millions per decade. Over a full century, you're in the range of billions of cycles on every spoke, joint and weld that carries that load. That is classic fatigue territory. Engineers can design for fatigue, but not for eternity. Small differences in manufacturing, tiny surface flaws, weld quality, bolt torque, all change how stress concentrates. A corner cutout here, a cable hole there, can boost local stress and give a crack somewhere to start. The longer you spin, the more those micro cracks grow, and the more you worry about what happens if one segment of the ring or one key joint starts to give way. If your rotating habitat is connected to a non-rotating core, where you might mount big antennas, main drives, or delicate instruments, you face another problem: bearings. A physical bearing that lets one huge structure spin against another is a nightmare over 100 years. Any classic bearing, with rolling elements and lubrication, will face wear, outgassing of lubricants and contamination. Dust from impacts, metal flakes from microscopic wear, and thin deposits from outgassed materials can all get into the contact surfaces. Even if you switch to magnetic bearings, levitating the ring in a controlled magnetic field, you are not free. Those systems require perfect alignment, stable fields, and precise control electronics. Slight shifts in structure from thermal cycles, small deformations from impacts, or long-term creep in materials can move things out of the narrow window where the magnetic bearing is efficient and stable. Now your no-contact bearing is fighting constant nudges, drawing more power, heating up, and potentially quenching if it involves superconductors. To dodge the whole giant bearing problem, some designs cut the ship in two. You put two modules on the ends of a long tether, spin them around their common centre of mass, and each end gets artificial gravity from the rotation. Good in principle, very bad when you remember the environment. A 1 kilometre tether, about 0.6 miles, only needs to be a few centimetres thick, an inch or so, if you build it from advanced materials in a lab. That might hold just fine during initial tests, and even for years in space. Now give it 100 years of micrometeoroid hits and dust impacts. Every tiny piece that grazes the tether can cut a few fibres, weaken one strand. No single hit snaps it, but over decades the safety margin gets eaten away. Thermal cycling makes the tether expand and contract, adding its own fatigue. Radiation and outgassing slowly change the material's properties. You can add redundancy, braided lines, multiple strands, but the more surface you expose, the more chances you give space to nick and erode it. A tether that looks safe with a 10-year test window on Earth might be deeply compromised by year 60 in interstellar space, and you only get to find out once. On top of all that hardware stress, there is your brain and inner ear. Humans do not tolerate high spin rates well. When the rotation rate climbs above about 4 revolutions per minute, Coriolis forces become a serious issue. Every time you turn your head, stand up, or move your arms, the moving frame of reference makes the motion feel twisted. People get dizzy, nauseated, some adapt, some never do. Long-term high RPM living carries serious risk of vertigo and weird adaptation effects. So designers aim for low RPM, like that 1 RPM example, to keep Coriolis forces small. But low revolutions per minute with near-Earth gravity means large radius. Large radius means more mass and more structure, which means more area to be hit, more metal to fatigue, more joints to monitor. You are trading human comfort for mechanical stress and maintenance burden. There is no free option. All of this leads to an uncomfortable choice as the decades roll on. The ring may still be spinning, the tether may still be holding, but the measured stresses and vibrations begin to creep upward. Sensors pick up subtle changes in the way the structure rings when small thruster firings happen. Crack detection systems maybe see hints of growth in one spoke or one joint. The bearings or rotation couplers draw a little more power. Engineers start to debate whether to keep running at a full 1G or to ease off. The easiest way to reduce stress is to reduce spin rate, because the loads on the structure go roughly with the square of the rotation speed. Drop from 1 revolutions per minute to 0.9 revolutions per minute, and the gravity you feel drops too, from about 1G to about 0.8 G. Similar to living on a heavy planet like Earth, but a bit lighter. Drop further to 0.7 revolutions per minute, and you are down closer to 0.5 to 0.6 G, between Mars and the Moon. The structure breathes a little easier, but now human biology pays more of the price. At 0.8 G, bone loss and muscle loss are probably less severe than in 0 G, but we do not actually know if that level is enough for a lifetime. At 0.6 G, fluid distribution in the body changes. Hearts may adapt in ways we have not seen. Children born and raised there may develop differently. You bought that lower mechanical stress by moving the crew further away from the gravity field evolution tuned them for. So the first failure in artificial gravity is not a loud snap or a ring breaking away. It is a meeting where the structural team says, for safety, we recommend a small spin reduction. That recommendation comes again 20 years later. Down the line, a generation grows up who has never felt a true 1G floor under them. The down they trust is one the engineers have quietly weakened to keep the ship from tearing itself apart. And while you are dialing down the spin to protect the structure from its own motion, there is another threat you cannot slow at all. The constant stream of high-speed dust and grit slamming into the front of the ship, eating away at the sacrificial shields that are the only thing between your Starship and hypersonic shrapnel. The dust outside is not the same problem as the dust inside. Inside, it clogs filters. Outside, at 1/10 light speed, it can punch through metal like it is nothing if you get the shielding wrong by even a small factor. Classical Whipple shields were never meant for this regime. Those are the systems we use now on the satellites and the ISS, with a thin outer bumper, some standoff distance, and then the main wall. At speeds of a few to maybe a few tens of kilometers per second, that works. A tiny grain hits the outer layer, breaks up and vaporizes, and when that hot spray hits the main wall, the energy is spread out enough that you just get a dent instead of a hole. At 0.1 C, roughly 30,000 kilometers per second, that picture breaks. A dust grain coming in at that speed carries energy that grows with the square of velocity. Compared to 10 kilometers per second, you are more than 1,000 times faster, so the impact energy per unit mass is about 1,000,000 times higher. At that point, the grain, the outer bumper, and a chunk of the main wall behind it can all be vaporized in one event. You do not just get a dent, you can blow a channel straight through thin structures. So interstellar designs end up with massive forward shields. Not a thin plate, but meters of sacrificial material in front of anything you care about. You might put 5 or 10 meters of water ice out front, or a deep bank of regolith, crushed rock scooped from an asteroid, or a layered block of metal foam. The job of that block is simple: stand in the way and die slowly, so that the habitable parts behind it do not. Every high-energy impact blows a tiny crater out of that shield. In ice, that means a bit of steam and ejecta shooting sideways. In rock or metal, that means a jet of vapor and fragments. Each crater is microscopic, but over 100 years with many millions or billions of hits of various sizes, the front face of the shield recedes. A 5-meter thick ice block might end up 4.5 meters thick, then 4, then 3.5, depending on the actual dust environment and your speed profile. The only way this is safe is if the designers massively oversize the shield at launch. You do not launch with just enough ice or rock. You launch with tens of % extra thickness, maybe double what basic calculations say, to cover uncertainties. If those starting assumptions are wrong, if the dust density is higher, or the typical grain mass is larger than expected, your 5-meter shield might erode like a 3-meter one in the models. By year 60, people on board could be looking at calculated remaining thicknesses that are uncomfortably close to minimum safe values. People have suggested smart shields to reduce the need for so much dead mass. Magnetic and electric concepts show up a lot. For example, an inflated magnetic field in front of the ship could deflect charged particles, creating a kind of plasma bubble. That helps for galactic cosmic rays and ions from the interstellar medium. It might also deflect some fraction of charged dust grains. But the dust that really worries you is mostly neutral or only weakly charged and much more massive than individual ions. A small rock speck or dust clump at 0.1 C does not care much about your magnetic field because it has too much mass and too little charge per mass. Magnetic sails are excellent for interacting with charged plasma, and they can be used for braking against the interstellar medium, but they do not replace a physical sacrificial shield against solid dust. At best, fields trim the higher energy charged population and maybe shrink the worst of the ionizing environment. The gravel still needs real armor. On Earth, we cannot test full 0.1 C impacts, but we do push projectiles to a few to maybe 10 kilometers per second using light gas guns or advanced pulsed power accelerators. Those tests already show violent cratering and spallation, where chunks of material break off the back face of a target even when the front is not fully perforated. The pattern is consistent. crank up impact speed by a factor of 10, and damage goes up by about a factor of 100 for the same projectile mass. Extrapolate that trend to tens of thousands of kilometers per second, and it is clear that any dust shielding scheme that is just enough at lower speeds is completely inadequate for interstellar velocities. The worst part of all this is that we do not yet know the interstellar dust environment at small scales with high precision. We have measurements from probes leaving the solar system, we have remote observations, but the detailed distribution of grain sizes, especially in the 1 to 10 micron range, still has significant error bars. If your designers underestimate the fraction of, say, 10 micrometer grains by an order of magnitude, that means there are 10 times more of those tiny bullets than your model assumed. Each one hits with a lot more energy than a single atom, but is too small to track individually. The shield gets eroded faster by impacts you cannot detect one by one. The same thing happens if the true relative velocity is a bit higher over parts of the route, or if you pass through an unexpectedly dense cloud of material. So what actually fails first in interstellar dust shielding is not a specific panel or a clear hole. It is the assumptions sitting under your models. Maybe in year 30, the onboard calculations show that your measured erosion rate is slightly above expected. Engineers tweak the model, increase the projected consumption of shield mass, and warn that margins are thinner than planned. In year 50, new data says the small grain density is still higher than any of the pre-launch scenarios. At that point, the crew must decide whether to reduce speed to cut impact energy, changing the mission timeline, or accept higher risk to the front armour. There is no spare 5-metre ice block waiting at a depot. This is a failure that you do not see with your eyes until it might be too late. The forward shield is buried in armour and sensor packages. You can send inspection drones and radar pulses, but there will always be some uncertainty in how much usable material is left and how damaged the internal structure is. The first time those assumptions are truly tested may be when a larger grain hits late in the mission, and how much of that energy gets through depends directly on whether your models were conservative enough. If the sacrificial front line is being eaten faster than expected, that feeds straight into the next risk. If you have to slow down early to protect the shield, your journey time stretches, and all the other aging systems are pushed harder. If you keep full speed, you gamble that your dust modelling was right. While the only way to know for sure is to keep flying into the unknown. And all the while, this same uncertainty is hitting the systems that link you back to Earth and tell you where you actually are, your communications and navigation, which also have to work across light years with shrinking power, aging antennas, and attitude control that is no longer as sharp as it used to be. You can fix a lot of hardware if you have time and tools, but what happens when the problem is that your ship is simply too far away to hear and only barely able to tell where it is? Every signal you send, radio or laser, spreads out as it travels. Think of it as a growing sphere of energy, the same total power spread over a larger and larger surface. The area of that sphere grows with distance squared, so the power per square meter drops very fast. Say your ship can push 20 kilowatts into a high-gain radio antenna, something like a big dish. Right out of the antenna, the beam is strong. A few light years away, by the time it reaches Earth, the fraction of that power hitting even a giant receiving dish is unimaginably tiny, way below what you can feel, only detectable after long integration times and very sensitive receivers. You do get some margin from using a narrow beam, good coding, and strong error correction, but every bit of degradation eats into that margin. If the antenna surface distorts a little as it ages, if alignment is off by a small angle, if transmitter efficiency drops by 10 or 20% as components age and run hotter, your received signal on Earth can drop below the level where you can push high data rates. Because of that, many designs lean toward laser communication for interstellar distances. Lasers can produce very tight beams, with divergences in the microradian range, a millionth of a radian. Over a distance of 4 light-years, around 4 times 10 to the 16th meters, a 1 microradian beam spreads to about 40 million kilometers, roughly 25 million miles across. That is wider than the orbit of Mercury, so you do not need perfect aiming at a single point, but you still have to point the beam, so Earth, or a relay system near Earth sits somewhere inside that cone. That means your attitude control and your navigation solution must stay accurate to a few microradians or better. That is an angle measured in millionths of a radian, like being able to point a laser from New York and hit a small target in Europe, night after night, with hardware that is constantly aging. Any drift in your gyros, any bias in star trackers, any flexing in the structure, holding the comms hardware, all add up. Over years and decades, those small errors push your pointing off center. The farther you are, the less steering error that you can afford, because the same angular mistake translates into a bigger positional miss at the receiver. Navigation itself leans hard on clocks. To know your velocity precisely, you measure Doppler shifts of tracked signals, you time light travel delays, you integrate small accelerations. Atomic clocks are fantastic by human standards, drifting by nanoseconds per day or less. But that is not the end of the story. Temperature swings, radiation damage, and aging of the resonant elements all push their frequency off over decades. You cannot just start a clock on day 1 and assume it is still perfect on day 20,000. You can and should cross-check your timing and position against external references like pulsars. Pulsars emit very regular pulses of radio or X-ray energy. If you can observe several of them and compare their arrival times to known models, you can get a fix on your position and velocity, a bit like a deep space GPS. But now your navigation depends on the stability of your pulsar detectors, your antenna pointing, your onboard pulsar timing models, and the software that matches observations to templates. All of those also age and drift. On top of that, your whole signal problem sits in a relativistic context. At 0.1 C, time dilation is modest, but real. Ship time runs maybe 0.5% slower than time on Earth. Over a century, that offset adds up to months. More immediately painful is Doppler shift. When the ship is moving away from Earth at a big fraction of light speed, the frequency of signals received on Earth is shifted down. When you are still accelerating or decelerating, the Doppler factor is changing. Communication protocols have to handle that continuously. You do not just lock a receiver to one fixed band. You have to track the changing frequency of the incoming signal as the ship speeds up, coasts, and slows down, and as your velocity estimate is refined. The same goes the other way for signals sent from Earth. If the software and hardware on either end misestimate the velocity, or if a bug creeps into the Doppler compensation code, you can easily end up transmitting most of your power slightly out of the receiver's band. The signal is still there physically, but the electronics are not tuned to catch it. As systems age and as patches accumulate, this becomes another place where bit rot bites. Early in the mission, a well-tested stack handles Doppler, relativistic corrections, and clock drift cleanly. Decades later, a quick fix for one odd condition interacts with hardware that has slightly different delays and clock offsets than the original design. Under some rare combination of velocities and attitudes, the link performance crashes for no obvious reason, or takes hours to reacquire lock. So what actually fails first in communications and navigation? It is not sudden radio silence. It is the richness of the link. In the early decades, you might be able to stream high-rate data back home, send video, detailed science dumps, continuous telemetry. The return link is strong enough, and both sides' antennas and lasers are fresh enough that you can afford wide margins. Navigation updates are frequent. Earth sends refined star catalogues and pulsar models. The ship returns precise attitude and clock calibration data. Over time, as antenna structures warp slightly, as pointing degrades, as transmitters lose efficiency, and receivers pick up more noise, your usable signal-to-noise ratio falls. You respond by increasing error correction overhead, by reducing raw data rates, by compressing more aggressively. Video becomes rare. Real-time conversation is out of the question because of light time delay anyway, but now even near real-time text becomes costly. Communication sessions stretch. Gaps between them grow simply because every bit you send is harder to pick out of the background. At some point, talking to Earth becomes a once-per-month, heavily planned operation. The ship transmits a compact status packet during a window when power, pointing, and systems are all lined up. Ground receives it, spends days or weeks decoding and analysing, and sends back a similarly compressed response. Navigation updates are less about continuous fine-tuning, more about occasional big corrections. The ship's onboard navigation and guidance must carry most of the load. Eventually, maybe late in the mission, there is a realistic chance that the link degrades to the point where only minimal beacons can be exchanged, or even stops completely, due to alignment issues, hardware failure, or simply the priorities of whoever is still listening back home a century later. At that point, your starship is not just physically far from Earth, it is informationally detached. It is, for all practical purposes, on its own. And that raises the hardest questions of all. When the data link back home is thin, when navigation is fully in local hands, when every major system is being run by people who never saw Earth, what keeps the crew aligned on the original mission? And what happens when the most complex, least predictable system on the ship, the human mind and human culture, starts to drift under century-long isolation? You can engineer steel and software, but how do you engineer a story that still feels true to people who have never even seen the planet that launched them? Psychology cracks fast, even on Earth, with support right over the horizon. Submarine crews, sealed in steel tubes for a few months, show increased depression, irritability, and sleep problems. Antarctic winter crews, cut off for a single season, report more conflict, more anxiety, slower thinking, and strange social dynamics by the time the sun comes back. Those are missions measured in months, maybe a year, with clear end dates, rescue options, and a huge support system outside. On a 100-year Starship, confinement is permanent for everyone on board. There is no getting off shift and going home. The ship is home. Every corridor is familiar by the time you are 10. Every face is part of a few thousand people you can never truly get away from. The scenery barely changes. You can redesign interiors, change lighting, move walls, simulate parks, but everyone knows those walls are still there. You can rotate people through different jobs, vary schedules, create festivals and rituals, but the constant background is that the world ends at the hull. For some, that will feel safe and contained. For others, over years, it will feel like a slow, dull pressure on their minds. You will see people who adapt, build deep identities as ship people, and people who do not adapt, who fall into apathy, anxiety, or self-destructive behaviour. Managing that generation after generation is not a side task. It is core engineering. Then there is the deeper shift, the fact that the people who launch are not the ones who arrive. The first crew signs up willingly. They believe in the mission. They have memories of Earth, of open skies and weather and distance. Their children do not. They are born into a closed world, with a mission story told to them from day one. To them, Earth is a word in a lesson, a picture in a file, not a lived experience. Over 3 or 4 generations, values change. Myths and priorities shift. Maybe the founding generation is obsessed with making it to the target star, no matter what. Their grandchildren might care more about daily quality of life on board, about fairness and culture. A generation raised during a long period of tight rationing and system failures might grow more conservative and risk-averse, or more rebellious and angry at the original plan. At some point, a generation will look at the navigation plots and the time left, and someone will ask out loud, why should we keep going just because they said so 100 years ago? Maybe a rogue planet or a brown dwarf with interesting resources shows up along the route. Maybe a faction argues for stopping there and building a new home rather than pushing on. Maybe another faction wants to turn back toward the home system or find a slower, safer path. That is not science fiction drama. That is a straightforward question of self-determination. Layered over that is population genetics and health. To avoid inbreeding problems, you probably launch with at least a few thousand people, or a smaller active population, plus a very large, carefully chosen genetic bank of stored gametes and embryos. With careful record keeping, strict guidelines on mating choices, and advanced genetic screening, that can keep the gene pool healthy. But notice how many perfects are hidden in that plan. You need perfect records, maintained over a century of hardware and software churn. You need continuous access to functioning labs, sequencing machines, storage systems, and trained experts who know how to interpret results and act on them. Any long-term breakdown there, even a 10 or 20-year period where those systems are weak, can let recessive disorders, harmful mutations, or skewed gene frequencies build up. The consequences might not show up immediately. They can surface as higher rates of certain diseases in later generations, subtle cognitive issues, or reduced fertility. All of this is unfolding inside a system that has to survive like no system ever has. History on Earth is noisy. Even robust democracies and long-lived monarchies see crises, coups, revolutions, reforms, and collapses on timescales shorter than 100 years. New ideologies appear. Charismatic leaders rise. Factions form and clash. Now put that into a sealed environment with no exit and finite resources. Your ship's governance system has to absorb power struggles without destroying the mission. It has to handle someone who builds a personality cult, or a group that wants to hoard resources, or a movement that rejects the founding plan. It has to keep legitimacy even if contact with Earth weakens or ceases. The "we are following orders from home" card will not work forever if home falls silent. Or, if the people on board no longer see Earth as an authority. You can design constitutions, councils, checks and balances, but every one of those depends on culture, on people believing the rules are worth following. You cannot send in a peacekeeping force from outside if something goes wrong. There is no neutral ground. Any crackdown or uprising risks damaging critical infrastructure because it is all built into the same finite hull. So what actually fails first in human minds and cultures? It is not necessarily open mutiny, it is consensus. At the start, the story is clear. We are here to reach that star. That story justifies sacrifices, risk and resource choices. It tells people why their daily work matters. Over time, that story can fade. It might be replaced by other narratives. We are here to keep the ship running. Or, we are here because we were born here, and this is our world. The target star becomes an abstract future, not a shared emotional goal. Do you spend rare metals on upgrading the telescope to survey the destination system? Or do you use them to build more comfortable habitats? Do you allocate extra power to high-gain comms with Earth? Or to onboard entertainment and education? Do you accept a slightly riskier shield-thinning maneuver to save time? Or slow down and extend the mission? Each choice can split along lines of age, profession, faction, or ideology. Engineers asking for strict maintenance windows and conservative margins can be painted as blocking progress or comfort. Leaders arguing to conserve resources for arrival can be accused of sacrificing current generations for a future they will not see. The same way arguments about budget priorities fire up people on Earth now, resource allocation and risk tolerance on the ship become flashpoints. But with life support, propulsion, and shielding sitting behind every debate, by the time you see open conflict about the mission itself, the subtle failure has already happened. The ship is still physically intact, but the people inside no longer share a single, strong answer to the question, why are we doing this? And if that answer crumbles, all the documentation, training, and engineering discipline that keep the ship's systems understandable across generations are at risk too. Because behind the hardware, behind the psychology, there is one more layer that has to last a century. The knowledge itself, the procedures, manuals, and mission purpose that tell each generation how to run the machine they inherited and why it is worth the effort. All of this hardware only works if every generation knows what it is, how it works, and why it matters. So what happens when the knowledge itself starts to age faster than the ship? Technical documentation is not timeless. It is written in the language, tools, and assumptions of the people who wrote it. Engineers in year zero use their current jargon, their current diagrams, their current file formats. They reference parts and standards that make sense to them. 50 or 100 years later, that language is not the same. Words shift meaning. Slang creeps in. Even plain language changes. On top of that, file formats and software tools rot. A maintenance manual might be stored as a specific type of 3D, CAD file, or a PDF with embedded scripts, or code comments tied to a version control system. If, 3 generations later, no one maintains the old readers or converters, critical procedures can turn into unreadable blocks of bits. You might still have the data physically, but no straightforward way to open and understand it. Without active translation and curation, your most important procedures can become arcane texts. A new engineer in year 80 might read a safety note written in year 5 and misunderstand a key phrase, because the original authors assumed knowledge that is no longer common. The risk is that manuals drift from being live tools to being like medieval manuscripts, technically present, but only half understood by a small number of specialists. At the same time, the education load on each generation is enormous. Every cohort of kids needs to learn basic literacy and math. Yes, but also spacecraft engineering fundamentals, ecosystem management, medicine under space conditions, governance rules, and the mission's history. On top of that, they will want to learn art, culture, and whatever new science and technology emerges on board. There is no outside university system to lean on, no billions of other people maintaining fields of knowledge in parallel. The ship's school system has to produce enough real experts in power systems, life support, structural analysis, biology, software, law, and more, every single generation, or gaps open. If schooling standards slip for even 1 or 2 decades, if a budget crunch or shift cuts investment in hard training, you may get a cohort with fewer true specialists. Those people then become the seniors in the next generation, teaching with weaker foundations. The decline is not obvious year to year, but over 50 years you can slide from "we truly understand this reactor" to "we know how to push these buttons and pray nothing weird happens." While formal knowledge fights to stay intact, informal stories evolve on their own. Human beings explain their world with stories, and those stories drift. After 4 or 5 generations, we launched from a blue planet called Earth. It is not a shared memory, it is something between a history lesson and a myth. Different groups on the ship might start telling their origin differently, emphasizing different lessons. One version might glorify sacrifice and obedience to the mission. Another might focus on how unfair it was that the first generation left everyone else behind. Another might downplay Earth completely and say, "This ship is our true home, the rest is old legend." If myths replace detailed logs in people's minds, decisions drift from data-driven to symbolic. Instead of asking what does the radiation dose map say, a faction might argue, "Our ancestors endured worse, we must be tough." Instead of, "What is the actual failure rate of this pump?" you get, "This module has always been lucky, we should trust it." Rituals and taboos can be useful to encode safety rules, but they can also ossify into habits that no one can explain, or be discarded because no one remembers the real physics behind them. We have seen this pattern on Earth over and over. Human history is full of technologies that were once routine and then were lost for centuries. Roman concrete had properties we struggled to fully match until recently. Greek fire was feared for its effectiveness, but its exact recipe and deployment methods vanished. Certain metalworking techniques, ancient dyes, navigational tricks all appeared were used, then disappeared when the last practitioners died, or when records became unreadable, or were ignored. Even in the 20th century, with global communication and huge institutions, NASA has struggled to read old data tapes, because the hardware and software to decode them were retired. Old source code written for specific mainframes became hard to run because the platforms and compilers were gone. That happened in a few decades, on a whole planet full of engineers. On a single starship with a few thousand people, the risk is higher. If one critical knowledge chain breaks, say the specific way to anneal a reactor component safely, or the full logic behind a complex life support control algorithm, you might still be able to keep the system running in normal modes, but you lose the ability to respond correctly when it behaves oddly. When an anomaly hits, the team reaches for documentation that is incomplete, in a half-forgotten format and full of assumptions no one quite shares anymore. That is how small incidents turn into big ones. So when you zoom all the way out, what fails first, really? It is not a specific metal part or a specific software module. It is the mission's cultural operating system, the shared story plus the body of knowledge that tells people what this ship is, what it is doing, and how to keep it alive. If that cultural OS crashes, if the story stops making sense, if the manuals become half-understood relics, if education thins out, then every physical system is sitting on borrowed time. You might still have a mostly intact reactor, but no one fully comfortable tweaking it. You might have life support hardware that could run for another 30 years, but no one willing to take the risk of a major overhaul, or no one able to read the original specifications correctly. You might have shielding that could handle a slightly riskier trajectory, but a climate that refuses to accept any perceived danger, or the opposite, a culture that shrugs off real risk because the origin story has turned into legend. Your 100-year Starship, in the end, is a bet. Not just a bet on alloys and semiconductors and control theory, but a bet that humans can maintain disciplined knowledge, honest records, and a shared sense of purpose longer than any individual machine can last. If that bet holds, then each local failure, an engine, a pump, a computer, can be understood and fixed or worked around. If that bet fails, if belief and understanding rot faster than metal and plastic, then the ship can still look physically solid on the outside, right up until the moment when some crew, staring at a screen they no longer fully trust, makes a decision that the original designers never imagined. In that sense, the first thing that really fails on a 100-year Starship is not the hull, the reactor, or the dust shield. It is the continuity of meaning, the thread of knowledge and purpose that tells each generation, in clear, simple language, this is where we came from. This is how this machine works, and this is why we are still aiming for that star. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.